All right, you guys. So today we are going to be looking at reactions for alkenes. I'm sorry I'm not there to do this with you in person, but I want to keep the material moving. And then if you have questions about this, things like that, we will review it when I get back. Okay. So for alkene reactions, the first that we are going to look at are addition and substitution reactions. Okay, so just like before with alkanes, how we had a variety of things we could look at. When you start adding in double bonds and triple bonds as we move forward, your options change. Okay, there are more things that can happen. And so that's where we're going to get started right now. So I want to first start us off with the addition of halogens. So what I would like for you to do now, actually, which is weird since I'm not there, but do it anyway. I want you to build the following. Okay, I want you to build 2-butene and also build Cl2. Okay, so that's what I want you to do first. And then I want you to break the double bond. And then I want you to attach the chlorines. So go ahead and pause and do that, please. Okay, so pause, build, do that. Okay, so hopefully what you saw was when you had that double bond in the middle of the 2-butene and then you broke it, it opened up that sort of space, that open space to kind of take those chlorines on, right? Like nothing was lost. There was no leftover. There wasn't like a switch, right? If you think about like when we were doing substitution reactions with alkanes, we ended up with like hydrochloric acid as a product. No, when we're talking about addition, you were literally like adding them on, and that double bond opens up, right? And it can take on those two little chlorines. So what we had was 2-butene, and then we had the chlorine. And then literally this double bond, right, like broke, and you ended up with these little bonds opening up, right? And so when that happened, you now had carbon, 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 carbon. Okay, I'm not drawing the H's for right now, just to make it clearer. So you had carbon, 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 and then it opened up, that double bond, whoop, opened up, and you were able to bring in those chlorines, right? So we had 2-butene plus chlorine, and that gave us 2,3-dichlorobutane. All right, there was no light or heat required, nothing like that. So I would like for you now to do is I'm going to give you the reactants and I want you to draw it out and name the products. Okay, so I'm telling you that we have 1,4-pentadiene plus 2 moles of bromine. Just give it a try, okay? Draw it out and see if you can figure out what's going to happen. Okay, so go ahead and pause again. All right, so hopefully you actually paused again. So pentadiene, so 1, 2, 3, 4, 5. 1, 2, 3, 4 pentadiene. And then we said we had 2 bromines. You don't need to draw it twice. You can simply draw it like that. And then 1, 2, 3, 4, 5. And then now we're going to actually be able to open both double bonds because we had those 2 moles of bromine available. And so all of those bromines can come on, which is going to leave us with 1, 2, 4, 5 tetrabromo pentane. The other important thing to note, y'all, is that the endings of these names become ANE, even though they originated as ENEs, okay? And again, that's because you're breaking the double bond, and so that parent chain is no longer a double bond, right? We don't need the ENE in the parent chain. Okay, so that was looking at addition of a halogen. Now I would like to do addition of water. This is actually something that happens a lot. It's how we make alcohols. So here we go. So it's going to be, you do need a catalyst here. Typically, you are going to have an acid as the catalyst for this type of reaction. Sometimes you'll see it just written as H+, because acids always contain a hydrogen. I don't care. I just want you to be familiar, you know, with both. Like if you were looking at it online or something, or soon in college, you'll see that H+. Okay, so water is going to add to the alkene. So what I would like for you to do now is we're going to build again. So humor me, I really hope you're actually building. Okay, call each other out, make sure you're building. I would like for you to build ethene. And I'd like you to build water. Right, H2O, just to be clear. Okay, so build those two molecules, and I want you to really think, and you can talk to each other. I want you to figure out what this product is likely to be. Okay, so you've got ethene and water, and I'm telling you that is an addition reaction. So go ahead, pause, build, and figure out what the product might be. All right, so we don't know how to name this product, but that's okay. So regular ethene looks like that, and water is actually HOH. So I know my Gen Chemers know this, that it's HOH. It's not actually H2O. I mean, they are the same thing, but the bond that is forming, the ions that are involved, are a hydroxide and a hydrogen. So you had ethene and water. We know that it's an addition. Didn't even change the color, but okay. So these open up, okay, and we've got CC, and then those double bonds open up. And so what's going to happen now, now that we've done this, is that the hydrogen actually adds on one, and the hydroxide adds on the other. So maybe you figured that out with building, maybe you didn't, but anyway, that is what's going on with the addition of water. And so this little OH, this is going to lead us into our next unit, which is called functional groups, but that little OH right there is what makes it an alcohol. So again, this process of addition of water, which by the way also has another name. It's also called, let's see, hydration reactions, but should make sense. You're adding water, hydration. That is another name for it. I just had that other writing right there that was in my way. But yes, a hydration reaction is another name for this, not to be confused with halogenation or hydrogenation, which we're also going to use. So lots of H's coming up. Anyway, so there's that. Another just quick example for your notes. Let's say we had cyclohexene plus water. And then we do have that acid. So again, you can write H plus or you could write acid. I apologize, I forgot to include that above up there. So H plus or acid, again, your preference. So now that ring breaks open, but we don't really need to show the H if we're doing a skeletal, but if it makes you feel better, you can draw it like that, or boop, 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 OH. So that was the addition of water. Now we are going to look at the addition of acids. Okay, so again, a reminder is that when you are talking about acids, they're always containing that hydrogen to start. So sometimes you'll see acids written as like HA, hydrogen acid. Okay, so just as a heads up there. So there are a variety of acids that can join in with double bonds. We are going to look at some of the more common, like sulfuric, acetic, hydrochloric, hydroiodic, but know that acids can do this, but there are some that are more likely than others to be involved in the addition with alkenes. Okay, so when we are doing this, let's just say a very generic, whatever, you're going to have your carbon double bonded to your carbon plus HA, where this is literally representing a hydrogen ion, and this is whatever your anion might be. Okay, that is then going to produce carbon, carbon, H, and then again, whatever that anion of the acid was. So again, like if you're talking about sulfuric acid, that whole sulfate piece attaches on in one place. So actually, since I keep talking about sulfuric acid, let's just do an example with sulfuric acid. So this is cyclopentene. I'm going to show you how sulfuric acid actually bonds. So often when we think about sulfuric acid, we think the formula H2SO4, which is true. That is the formula for sulfuric acid. But if you actually were to sit here and build it, you would actually see that it's kind of the hydrogen gets attached to one of the oxygens, and then there's the sulfur that attaches to 3 oxygens, and a hydrogen. So this is actually, I'm just writing it this way because I think it's more visual for you to see. I don't need you to write it this way. You're welcome to write H2SO4. But a lot of the spirit of this class is to get you exposed to different ways of seeing things so that you're ready when you were to take this in college. You'll be like, oh yeah, I remember seeing that weird OSO3H written out. So anyway, I'm writing it that way. Again, feel free to write it H2SO4. That is the formula. And then what is going to happen is that double bond opens up. Boop, okay, and then it snatches the cation, which is always a hydrogen, and then whatever the anion is. So again, I'm writing it OSO3H. Feel free to write it instead as HSO4. Okay, it's fine. All right, it doesn't matter to me. But again, I'm just showing you the correct format for it. All right, so here are some for you to do. I'm going to tell you that it is 2-butene and hydrochloric acid. And let's do 3-hexene. And my favorite acid, hydroiodic acid. All right, so go ahead and pause, and I would like for you to draw the structures for your reactants and your product. And then for these 2 examples, you can also name your product. So again, go ahead and pause and do that, please. Okay, so here you go. Here are your answers to that first part and second part of your problems. Again, I'm drawing skeletal for me here. I think it's a little bit easier for me personally, but it doesn't specify. So if you drew out structural, things like that, no worries. Okay, structural, condensed, whatever. But again, I do want to take a second to point out, make sure you changed that ending to ANE and not ENE. Now, whether you had your iodine here, or your chlorine here versus here, the names were still going to be the same. 2-chlorobutane, 3-iodohexane. Great. This leads us into our next topic of what happens when they might not be the same. So what I would like for you guys to do now is we're going to do another pause and build. So do it. Hear me. Hopefully you guys are all on a similar pace, because this is one of those times where I want you guys to compare your models and hope that somebody built something different. So here we go. What I would like for you to do is to please build propene And we're going to do water. Okay, so build propene and please build water. And then I'm going to tell you, right, in the presence of an acid, right, we need our catalyst there for hydration. Okay, we're in the presence of acid. I want you to build those two things and build me your products. So go ahead and pause, build propene, build water, and then build what would happen. You're going to build the product. And then hopefully you can compare with some people around you and just see what you guys each built. Okay, so when you built these friends, right, we had CH3, CH, our double bond, and then our CH2 plus water. And my hope is that maybe in the class, you guys ended up with different models, or even on your own, you figured out like, oh wait, I could do two possible things, right? So we have this acid, H, you could write H acid, right? Just indicate to me somehow that you know there's an acid involved. We could break that bond and you could add you could have added the hydrogen here, and it was H, so now it's CH2. Or you could have added the hydrogen on the end, which was CH2 is now CH3, right? So that double bond opened, and you could add the hydrogen one way and the OH to the other, or H here and OH here. Okay, and if that was the case, if we did the first, then we'd have an OH here. If we did the second, then we have that OH there. Okay, we have two potential products. Okay, these are possible. They are called regioisomers. Okay, and so for regioisomers, we're going to move with this. If it is regio specific, then that means only one of the two possible products actually occurs. Okay, so regio-specific means only one of the two potential products actually will form. So like here, we had two potential products. If it was regio-specific, then that would mean that actually only one of them happens in real life. So that's regio-specific. And then regio-selective is our other option for regioisomers. Come on, pen. Regio-selective. Okay, which means both are possible. One is more likely to occur. Okay, so both are possible, but one is more likely to occur. And so when we look at this, we use something called the Markovnikov. Markovnikov fancy rule. Okay, and we say when an unsymmetric reagent, okay, when an unsymmetric reagent is added to an unsymmetric alkene, the cation part, okay, the real word they use is electropositive. We don't need to talk about that. The cation part, which is typically a hydrogen, okay, bonds to the carbon of the double bond that has a greater number of hydrogens already attached. When an unsymmetric reagent is added to an unsymmetric alkene, the cation slash electropositive slash hydrogen ion part bonds to the carbon of the double bond that already has a greater number of hydrogens attached. That is the rule that we will use if something is regiospecific. So let's talk about what symmetric versus unsymmetric means, like mirror image versus not. So symmetric, 2 M's, symmetric, I think so. Symmetric, if you had like bromine to bromine, chlorine, chlorine, H, CH2, double bond, CH2, CH3, CH2, double bond, 1, 2, yeah, CH2, CH3, even a pentene, right? If we were to draw a line through those, either half are symmetric, right? Like you fold it in half, boom, same thing. If we were then to do unsymmetric, asymmetric, unsymmetric, that might be something like HBr, HCl, HOH, HOSO3, CH3, let's actually do it all on a line though. CH3, CH2, double bond, CH3, double bond, CH3, I don't know. You draw that line. They are not mirror images on either side of that line. They are considered unsymmetric. And so these things over here are likely to give you those regioisomers. God is writing on a computer screen. It's like writing on a whiteboard. Regioisomers. Okay, so we'll keep going. Let's say we had something like, let's just do a generic thing for your notes. Okay, C double bond C, and then you have your H's, whatever they might be, plus something that is unsymmetric. Now you have R to C, and you had your H and your H already there, and your H there. Keep in mind, when we write formulas, our positive thing is always first. So this one right here, right, it has 2 H's there. And so your positive is going to go there. And your negative is going to go there, if it's regiospecific. If it's not, both are possible, right? You could put the H, the X, or the Y either place. But if it's regiospecific, notice how on this side, right, we have 2 hydrogens attached to this carbon. So therefore it has 2 H's. It's got more H's, so positive thing goes here. Very scientific wording. Okay, I just realized I wrote that wrong, because there's no way that that right there now has 5 bonds. I'm so sorry. Because it would be CH3CH double bonded to CH2 plus hydrochloric acid. So CH3CH, or CH3CH, Then you're bringing in, you could do the hydrogen here, or you could do the hydrogen here, in which case the chlorine would go on the others. So now that I've written this correctly, because I knew the chlorine was not supposed to be on the end, when we look at this friend, the way it is written now, we want to see that that chlorine is actually going to go here in the middle, because there are two hydrogens there as opposed to only one hydrogen there, right? So there's one hydrogen here, two hydrogens there. So this, this is the one that would occur if it was regio specific. Let's have one more without drawing both products. Let's say we had CH3, C double bond, CH2. Let's throw in a methyl group. Okay, and we're going to do it with water. So I am going to have that acid written here. So I have CH3 to C to C, H2. CH3. So then when I think about what my changes might be without having to draw the other, I notice this is where my double bond was, okay? And so this carbon has two hydrogens and this one has none. So the hydrogen is going to go there and my hydroxide is going to go here. Again, this friend had two hydrogens and this one had 0 H's. So two more hydrogens, that meant the hydrogen bonds here. All right, so we're gonna put up some practice for you, and then that is it for today.